The Freon-based heat engine, known as the Drinking Bird, is popularly used in primary and secondary schools for its playful design and deceiving appearance of perpetual motion. However, the toy actually demonstrates many of the basic principles of thermodynamics, heat cycles, and mechanics, similar to those found in heaters and refrigerators. While all of these phenomena are well documented, little data exists on the effect of changing the temperature of the bird's glass of water. In this video, we hope to elucidate the basic principles behind this bird and use them to explain the results of this previously untested experiment. People have been fascinated with the idea of the perpetual motion machine for centuries. However, as appealing as these ideas are, their impossibility is made clear when one considers the laws of thermodynamics. The first law, which you are probably most familiar with, says that energy can be neither created nor destroyed, essentially that a system's energy cannot increase or decrease without contact with an outside source. In this example, this chair starts at rest. It will not move until Ashley adds energy to the system. Most perpetual motion devices violate the first law, as moving parts by definition lose energy, most notably to heat caused by frictional forces. This means that a machine cannot maintain constant energy as an isolated system. Without outside energy being added to the system, the machine will eventually come to a halt. In this experiment, we will investigate the Drinking Bird, a mechanism which could also be mistaken for a perpetual motion device, though of course by now you know there must be more to the story. This is a drinking bird. You've probably seen one before, but have you ever stopped to consider how it works? To start, let's look at the design. The body consists of two spherical bulbs, a larger bulb at the bottom of the bird and a smaller bulb at the top. Connecting the bulbs is a tube, which in turn is held by the hinge which allows the body to oscillate. A volatile fluid such as Freon 11 is encapsulated within the bird. This fluid is often dyed so its movement is easier to see. To start the oscillations, the beak of the bird is wetted in a glass of water. The beak is made of a spongy material which allows for a relatively large amount of water to be stored within. Energy is exchanged in the system by two methods. When water evaporates, it draws energy from the system in order to change state from a liquid to a vapor. This withdrawal of energy from the system cools down the beak, the same principle that explains why we sweat when we're hot. Additionally, the difference between the temperature of the water and the upper glass bulb causes a loss of energy. The combination of these energy losses leads to cooling on the surface of the glass bulb through conduction, followed by condensation of the Freon 11 vapor via convection. The loss of gaseous Freon 11 due to condensation decreases the vapor pressure in the head by the ideal gas law. Liquid Freon 11 is driven up the tube by this pressure differential due to Bernoulli's principle. The bird becomes top-heavy and tilts forward, dipping its beak into the glass of water. The now condensed Freon 11 in the head of the drinking bird falls back down to the lower bulb as vapor bubbles move up the tube and into the head. This reverses the weight distribution, making the bird bottom heavy. This oscillation continues until there is no water left to cool the bird's beak. At this point, friction at the hinges and air resistance will bring the bird to a stop. The water's interaction with the bird is why the mechanism cannot be considered a perpetual motion device. Though the bird at first appears to be self-propelled, it is actually the temperature and pressure gradients caused by the evaporation of the water on the beak and conduction which drive the bird's motion. Now that we understand the mechanisms by which the drinking bird oscillates, we may begin to see these principles in action. For this experiment, we used cups full of water with temperatures ranging from cold water at 10 degrees Celsius to warm water at 40 degrees Celsius. To start the cycle, Patrick takes the bird and dips its head into the water, saturating it. We allow the bird to oscillate 10 times in each cup of water, during which time we record the total time with the stopwatch. After recording all the times, we divide by 10 to calculate an average experimental period. After testing, we observed that, starting at very low temperatures, the drinking bird oscillated rapidly. As temperature increased, the oscillations began slowing, reaching a maximum period of oscillation at 15 degrees Celsius, before beginning to again increase in frequency. The period of oscillation reached a minimum at room temperature, about 25 degrees Celsius. As temperature further increased, we observed a similar slowing and then quickening of oscillations. This trend can be explained by heat transfer principles. As explained previously, when water evaporates, it removes heat from the system. As temperature increases, the rate of evaporation, and therefore the rate of heat removal, increases. This causes the frequency of oscillations to generally increase with temperature. However, when there is a difference between the water temperature and the head of the bird, conduction occurs. This causes either a removal or an addition of heat to the bulb. The final result is the function shown here. As previously mentioned, the drinking bird's oscillations are induced by heat transfer from the bird's body to the water evaporating off of its beak. It is a great example of a seemingly physics-defying case of perpetual motion, which in reality can be explained using simple heat and mass transfer principles such as conduction, convection, and diffusion. Use this modest experiment to educate your friends on the merits of investigation, or make them marvel at your acute knowledge of black magic. In either case, as a future chemical engineer, your new insights into the impossibilities of perpetual motion will surely stop you from proposing equally impossible designs in your own career. Thank you for watching.